Is that clear?
Yes.
I just have a question. Because you started with the beam and you found the moment for the beam by looking at how it was bending. If you do that for the column, though, the moment's going the opposite direction than the way it's bending. So that's just confusing me because I don't know. Could you do the same thing starting from the column and going up?
Good question. That's a very keen observation. The approach I started with is always start with the horizontal members.
Okay.
If you follow the procedure, you always have to start with the horizontal members.
Okay.
Because that doesn't apply to the column. Another way to explain that, why can we only look at that here? Why can we only look at this one at the beginning? Why? It's because when we start with the analysis of the beam member, which is element AB, there's no effect of P, right? If you look at this one here, there's no P here. Everything is just by itself, which is this. No P. Why the P effect is complicated? Because once you have the P acting on the column, you cannot use the same principle.
Okay.
To judge. In this case, actually, the reason why it bends that way is because of the force, not necessarily because of the moment.
Okay. So if the force was horizontal, then you would want to start with the column?
Right. I guess the more theoretically correct answer is you should start with the element without the effect of the applied force.
Okay.
Because when there's no applied force, you can just look at the shape and to determine the direction of internal moments. That's not the case for the column, because even so that the internal moment is going in the opposite direction, but the column is going to bend that way because of there's another force, P, acting on the column. So we cannot start with the column because you have two different effects. You have internal moment, you also have external force, and that will complicate our assessment.
Okay, thank you.
Is that clear?
Yeah.
Okay. All right, so this is the first example. And the next example I'd like to show you is this. Look at example 2. And this is what, page 7, right? Page 7. And let's look at example 2. So what's example 2? Example 2 is the Timoshenko beam column with a concentrated lateral force. And what is Timoshenko beam column? Timoshenko beam column means that the vertical deflection caused by the shear force or shear stress can be ignored in calculating the deflection of the column or the beam. That means even so there's a shear force acting inside the column, but we're going to ignore it. And in this case, the force is actually acting from the right. So let's put the force here. Force acting like this. And of course, we have to define everything. You need to define the span. Let's say that the total length is, choose the wrong direction. The total span of the column is denoted by capital L. And there's also another force acting somewhere. So there's also another force, let's call it Q, because P and Q. And this Q force is acting at the distance from one of the supports of this value C. Let's call it that way. And because we already call this A, we call this B, so this distance gets to be the C. And we also have to define our x and y's, and that's important. So our x-axis will be defined from the point A. If you go horizontally, this is our x-axis. And the y-axis will be the direction. Of course, we can choose which direction to use. In this case, we want to choose the positive direction, which we know that this beam column will actually bend downward, right? Due to the application of the force Q. Therefore, we know that this is the positive direction of y we're going to use. So that's the y direction we defined. Now, our objective is what? Is to determine the PCR. I will just call it PCR of this beam column. Remember, why do we call this a beam column? We call this a beam member because of the force Q. We call this a column member because of force P. When you have both P and Q, this kind of force, one is along the longitudinal direction, the other is perpendicular, this will constitute a what we call beam column element or the beam column member. So let's solve this problem. Start with step one. Step one is always to form the free body diagram. You already know FBD. So what's a free body diagram? If we just take one part, which is right here, or use this, you take one part right here to form the free body diagram. And it looks like this. One of them is your support, and the beam is going to bend like this. From here, you have the variable which is x, and this is your y. Internal actions. When the P is applied here, you have another P acting here. That's reaction, not action. And also internally, in order to balance this force P, there must be another force acting here. I am going to use a thing because this place is going to get a little bit messy, right? Force equilibrium tells you that if the reason why we have this thick force P is because of the external force acting at point B. So the force developed at point A is because of the force acting at point B. Now, equilibrium dictates us to have another P here. And at this end, which is where we cut it, there's no force acting here. That means the internal moment must be going like this. Now, in addition to this, we will also have the vertical force. If you have a vertical force applied here as a Q, and from structural analysis, we also can determine the reactions at point A and point B, right? We also know that. So the reactions at point B, if you still remember, is inversely proportional to the distance from the point to the nearest support. So here it is actually C over L, but it's inversely related. That means it should be C minus L minus C. So that is L minus C, the whole thing times Q. And the other one, the reaction at point A is going to be, you already know, it's just going to be C over L times Q, right? We know that from structural analysis. Now, of course, because of that, we know that at point A, the reaction is C over L times Q, right? Now, what we're going to do is to take the moment equilibrium at where we cut the free body diagram. So the moment equilibrium is will take place at here. This is where we're going to take moment equilibrium. So let's take the moment equilibrium. Summation of the moment must be 0. And you can choose whatever the direction you want. It's better that you write down the definition. I always instruct students to do that. Suppose we use clockwise direction as a positive direction as moment. So you write this down, something like this. So you know that whatever is a clockwise, produces a clockwise bending moment, we will take as a positive. So by taking the moment here, we have 3 quantities we have to consider. And first, of course, this is another internal moment, which is what we call internal moment here. Right. So what are the 3 quantities we have to consider? The moment that you can consider, the terms that will produce a moment at the point inside this beam column, there's only 3 terms. One is the moment produced by this force, 1. And the moment produced by the reaction at point A, correct? Which is this one, 2. And the third one is what? It's just internal moment itself. That's going to be the 3 terms we're going to put in here. So by taking the moment equilibrium, you can put it this way. The first term, which is Q times C over L, that is the first force, which is this one. And what is the moment? And the moment is actually the force times the distance. So what's the distance? The distance in this case is actually x. This is x. From here to here is on the x-axis. So here, force times x. That's clockwise, so it's positive. There's also another force, another moment produced by the force P, right? And what's the distance? Distance is y. So from this point to this point, that is actually y. From here to here, if it's not clear, this is y. And from here to here is x. And then we will know that the moment produced by the force is also in the clockwise direction, right? But the quantity is P times Y. So this will become P times Y. And the whole thing must equal to the internal moment, which is M internal, like this. So that's the moment equilibrium. And we'll do the same for another element, which is from the other end, avoiding this vertical force Q. So if you consider another one, which is from point B, this is the free body diagram. We already know that there is a force P here. Internally, there's a force P here. And we also already know that in the vertical direction, this is L minus C divided by L times Q. And the direction of the internal moment, which is this one here. That's internal moment.